Mhm. So let's start today's class. In this week, the course content, that is the heat transfer, we had discussed about heat exchangers. So we basically started with the introduction to the heat exchangers, different types of heat exchangers. Then we covered parallel flow heat exchangers, in which we discussed about counter flow, co-current flow, different kinds of flow. Then we covered this concept of log mean temperature difference, also known as LMTD. Then we discussed about the Shell and tube heat exchangers. And then in the direction towards calculating the performance of heat exchanger and design of heat exchanger. Heat exchangers, we discussed this epsilon and TU method. So this is a basic schematic of a heat exchanger, whereby you can see that these all are the tubes through which the fluid can flow, and this entire outer vessel is known as a shell side. So one fluid will flow through tubes and the other fluid will flow through the cell side. Now it is up to you whether you want to take whether you want this hot fluid inside the cell or hot fluid inside the tube. However, there are few thumb rules that you can take a look on while deciding which fluids should go via which route. So for example, in this diagram, I have shown that the hot fluid is passing through the cell side and the exit is shown over here, whereas the cold fluid is entering via this side through the tube and exiting via this. Similarly, if we take a look on this graph, which shows the temperature variation across the flow direction. So if we are considering this hot fluid, the flow direction is in this direction. So initially the hot fluid will be at a higher temperature. As we move in the flow direction, the temperature will decrease. That is what is shown in this temperature profile. Similarly, for the cold fluid, we can see that as we move in along the flow direction, the temperature of the fluid will increase. The temperature of the cold fluid will increase. Then we have this different kind of parallel flows. Different kind of flows. The first one is parallel flow, also known as also known as co-current flow, in which the fluid will flow in the same direction. Similarly, in case of counter current flow or counter flow, both the fluids will move in opposite direction. Then there is this concept of passes. So for example, if this blue denotes the cold fluid, so over here you can see that it will take two pass along the entire shell side. So that is why we call this as two pass and single shell side. So for example, over here, this is our shell. So if my cold fluid goes via this route and again comes via this route, so basically inlet is over here and outlet is also over here, but it will take two pass between this. So we can call this as two times tube pass and one time shell pass. Such a kind of fluid such a kind of flow we can say, such kind of heat exchanger. Then if we draw this temperature profile for this co-current as well as counter current flow, you can see as shown in the figure, initially at the inlet, the temperature difference will be higher, but as we move along the flow direction along x, the temperature difference will decrease. Similarly, in case of counter current flow, you can see the temperature difference at the inlet will be different and at the outlet also it will be different depending on the fluid property. This is the flow rate and the temperature of inlet outlet. It can vary, but again the main thing you need to focus is the direction of the flow. So in the co-current flow, the flow is shown in the similar direction, whereas in case of counter current flow, the flow is in the opposite direction. Then the main motive behind this heat exchanger calculation is to first evaluate the heat exchanger design, that is basically calculate the effective heat transfer area, and the second is the performance calculation, that is how effective is our heat exchanger in order to cool or heat the fluid through which it is flow for which it has been designed. And then we have this overall heat transfer coefficient. So that is, if the overall heat transfer coefficient is U, then we can write using the concept of resistance as 1 upon UA is equal to 1 upon HIEI. Then this is due to the fouling on the inner side. Then again due to the conduction. Then again this is due to fouling on the outer side, and the heat transfer coefficient resistance due to the outer side. So in the figure, you can see the actual fouling that has been shown on the outer side, whereas this figure shows the fouling on the inner side. So due to this fouling, you can see that the effective resistance to the heat transfer increases. That is why we take into account of this term. Then if we write a differential energy balance across either of this parallel flow and counter flow, then we can define this driving force, that is a temperature difference, as log mean temperature difference, which is given by this equation, that is delta T2 minus delta T1 upon ln of delta T2 T1. That is our log mean temperature difference. So for example, in case of, let's say, counter current flow, you can say, let's say if the temperature of the cold fluid is some fixed temperature, so eventually it will keep on decreasing. However, if the temperature of the hot fluid is some TH, TC in, TC out, TH in, and TH out. So over here you can see that the delta T of this term is very high as compared to this. That is, the temperature difference across the length of the heat exchanger will keeps on changing. That is why, in order to account for such a variation in temperature difference, we define this kind of average log mean temperature difference by this equation. Then, in order to characterize the performance of the heat exchanger, we can define this Q max, that is the maximum possible heat exchange that can occur through the heat exchanger, by this equation, that is C minimum. C minimum is nothing but the minimum of CH upon CC, where CC is nothing but mass flow rate of the coolant, or mass flow rate of the cold fluid into the heat capacity of cold fluid. Similarly, CH is the mass flow rate of hot fluid into heat capacity of the hot fluid. So the maximum possible heat transfer through any heat exchanger will always be given by this equation, that is C minimum into temperature of hot fluid inlet minus temperature of cold fluid at the inlet. Now it won't matter if it is co-current or counter-current flow. We will only consider whether it is a hot inlet of hot fluid and inlet of cold fluid. So on the basis of this, we can define the effectiveness factor as Q upon Q max. That is, Q is the actual heat transfer that is occurring either in the cold fluid or the hot fluid upon Q max. So Q, if we are considering cold fluid, it will be Cc into Tc output minus Tc inlet upon the maximum possible heat transfer. Similarly, if we are considering hot fluid, then effectiveness will be Ch upon Thi, 1 Th0, and this. Ultimately, both of these effectiveness factor will be similar. Then we define this new parameter as a number of transfer unit, or NTU. It is nothing but it is a ratio of conductance to the minimum heat capacity rate given by this. That is, NTU is equal to UA upon C minimum. So this NTU will be useful to calculate the effectiveness of the heat exchanger. So if we have to calculate the effectiveness of heat exchanger, then we can have certain correlations that correlate this NTU with this heat effectiveness. So these equations will be provided to you. And also, if we have the C minimum is equal to CH, then you can write the effectiveness by this equation. So basically what you need to do is, both of the C minimum is equal to CH. So you can just cancel. So basically you can just replace this epsilon upon C epsilon upon this term over here, and since Cc is equal to, then you can basically ultimately cancel this CHCC, and then you can get this desired ratio that has been shown. So this concept we will study in the numerical, and it will be more clear to you. So let's start with solving the questions for today. So this is question number 1, which states that consider a concentric tube heat exchanger characterized by uniform overall heat transfer coefficient and operating under the following conditions. Mass flow rate of hot and cold fluid is 0.125 kg per second. If a counter flow heat exchanger is operated under the same situation, what is the ratio of required areas for these two flow conditions? That is, we have to find the ratio of counter flow upon parallel flow for the given concentric tube heat exchanger. So let's try to solve this question. So over here, we know that the overall heat transfer rate will be equal to Q is equal to UA delta T, which is where delta T is LMTD. Now, in this given question, we have been given that the counter flow as well as the co-current flow are operated under the similar condition, and for that we have to find the heat transfer. So if they are operated under similar condition, we can say that U as well as overall heat transfer coefficient as well as the heat transfer rate will be similar. So if we have to find the ratio of this counter flow as well as this co-current flow or the parallel flow, you can just write this as Q of co-current counter current flow upon Q of parallel flow, that's co-current flow, will be equal to, U will remain same, ACF on APL delta T LMTD of CF on delta T LMTD of parallel flow. Again, this U are same as well as Q will be same. That is, we can write ACF on APF is equal to delta T LMTD of parallel flow on delta T LMTD of counter current flow. Now, using this, you can calculate the log mean temperature difference from the given figure, and then you can calculate the desired area. But now, if you see, if you have to calculate this log mean temperature difference, you need all the four temperatures, that is inlet as well as outlet. But in this case, you can see we have the hot inlet temperature of the hot fluid, but we don't have the outlet temperature of the hot fluid. So we can straight away write a simple energy balance, that is Q of hot fluid will be equal to Q of cold fluid. So this will be equal to mass flow rate of hot fluid, Cp of hot fluid into delta T of hot fluid is equal to mass flow rate of cold fluid, Cp of hot fluid into delta C of cold fluid. So this will give you, we have been given the mass flow rate of both the hot and cold fluid are same, so we can just cancel them out. Heat capacity of hot fluid is given as 2100. The temperature difference will be 210 minus Tc outlet we have to find. Cp of the cold fluid is 21 is 4200, and the temperature difference there is 95 minus 40 is 55. So this will be around 2 is equal to 110. So this will give us Tc0 as 100 degrees Celsius. Now, if you have to calculate the LMTD, so let's just draw this for, let's consider case of counter current flow. If this is our hot fluid, this is our cold fluid. So we saw that the hot fluid will go from 210 to 100 degrees Celsius, whereas the cold fluid will temperature will rise from 40 to 95. So if we take a look on this delta T1 over here, so delta T1 will be 210 minus 95, that is 115. Similarly, delta 2 over here will be 60 degrees Celsius. So LMTD So delta T Lm for counter current flow will be delta T1 minus delta T2, that is 115 minus 60 upon ln of 115 upon 60. So this should come. So this will come around 84.54. Similarly, for parallel flow, where both are flowing in the same direction, if this is my hot fluid, where temperature goes from 210 to 100, and for cold fluid, temperature will go from 40 to 95. You can calculate again the LMTDS delta T over here will be 170, and that over here it will be 5. So delta T Lm for parallel flow will become 170 minus 5 upon ln of 170 upon 5. So this will come around 46.79. So the desired area in the question that we were asked to find was ACF upon APF. So delta T for parallel flow, we calculated it as 46.79 upon 84. So 46.79 upon 84.5. So this ratio will approximately come around 0.55. So that is the area. So from over here, you can see that the area required in the parallel flow will be higher as compared to the area required in the co-current flow. So for the given system, we can say that the co-current, the counter flow will be beneficial, because in the parallel flow, the area required is almost twice of that. I hope this solution was clear. So now let's move on to the next question. So over here, we have been given a two fluid heat exchanger. So we have been given, so that is two fluid heat exchanger has inlet and outlet temperatures of 65 degrees Celsius and 40 degrees Celsius for the hot fluid, and 15 degrees Celsius and 30 degrees Celsius for the cold fluid. Determine the effectiveness of the heat exchanger. Consider C minimum is equal to CH, where C stands for m dot Cp. So in this question, we have to find the effectiveness of the heat exchanger. So the formula for effectiveness we saw as effectiveness is given as Q upon Qmax, and Qmax is given as C minimum upon T hot inlet minus of Tc inlet, whereas this Q is given as whatever fluid you want to consider, that is CH upon THI minus of TH0. Since this question we have been given C min equal to CH, we consider this hot fluid, or else we could have considered the cold fluid also. Now if we take a ratio of both of this term, epsilon, that is effectiveness factor, we will be getting as CH upon THI minus of TH0 upon C minimum upon THI minus TCI. Now C minimum is equal to CH, so we can just cancel it out, and then we can replace all the remaining values. So the hot fluid inlet is 65 and outlet is 40. So the difference will be 65 minus 40. Similarly, the cold fluid inlet is 15 degrees Celsius. So this will come around 65 minus 40 is 25 upon 50. So this will come around 0.5. So the effectiveness of the heat exchanger in this case is 0.5. Now let's move on to the third question. So try reading third question. I will discuss the solution in a couple of minutes. Let's see, in 10 minutes we can discuss the solution. So basically in this question, you have to find the overall heat transfer coefficient from the formula that I had shared earlier. And in order to find the overall heat transfer coefficient, you need to find the outer heat transfer coefficient for the tube side as well as inner heat transfer coefficient for the tube side. For that, you can use the Nusselt number correlation or the Dittus-Berger correlations, depending on the value of Reynolds number that you obtain. So let's try to see the solution of this question. So So in this question, we are given that saturated steam at 0.14 bar is condensed in a shell and tube heat exchanger with one shell pass and two tube pass consisting of 130 brass tubes, each with length per pass of 2 meter. The tubes have inner and outer diameter of 13.4 mm and 15.9 mm respectively. The cooling water enters the tubes at 20 degrees Celsius with a mean velocity of 1.25 meter per second. The heat transfer coefficient for condensation on the outer surfaces of the tube is 13500 watt per meter square Kelvin. Determine the overall heat transfer coefficient. So we know that the overall heat transfer coefficient for this heat exchanger, whereby where we know that the overall heat transfer coefficient is given as 1 upon U naught. Now, the overall heat transfer coefficient, you can write U naught as the inverse of 1 upon H naught plus 1 upon Hi plus 1 upon Hi. Since we are considering U naught, it will become R naught upon Ri. And this will, due to conduction, it will become R naught upon Ln of R naught upon R1. Now, in the given question, we have been given the heat transfer coefficient for condensation on the outer side of the tube is this. Basically, we are having this term, but we don't have this Hi. So basically, we don't have the tube side heat transfer coefficient. So for that, we can calculate it using the Nusselt's number correlation. But in order to use that first, we need to calculate the Reynolds number. So the Reynolds number for this case will become rho Vd upon mu, whereby the density of the fluid is 995. The velocity of the fluid is 1.25 meter per second. Into the diameter is 13.4 upon 13.4 mm, and the viscosity is 769 into 10 raised to minus 6. So if you calculate this, the Reynolds number will come around 21673. So since this is a turbulent flow, we can use the Dittus-Boelter correlation in order to find the tube side heat transfer coefficient. So that is given as Nusselt's number will be given as 0.023, Reynolds number into 0.8, Prandtl number into 0.4. So Nusselt's number is nothing but Hi diameter upon K into 0.023 2163 into 0.8 upon Prandtl into Prandtl number is 5.2 into 0.4. So this term should come around 130.88. From here, you can calculate the value of Hi as 130.88 into K is 0.620 upon diameter 1 This inner side was 13.4 into 10 raised to minus 3. So the value of HI from this should come around 6055. So this value now we can put over here and just calculate, so we can get the answer as, so 1 upon H naught we have been 1 upon H naught we have already been given, so it is 13500 plus 1 upon HI we calculated over here as 6055 into R naught upon R1. So outer diameter is 15.9 upon inner diameter is 13.4 plus R naught is again 15.9 to 10 raised to minus 3 mm, and K we have been given as 114 into ln of, you can write this is 15.9 upon 13.4. This you can calculate, and the overall value of the overall heat transfer coefficient U naught will come around. You have to take the inverse of this, just remember inverse of this. So this will come around 3546 watt per meter square Kelvin. So you can try calculating this on your own, and then we can move on to the next question. So the model solution for this is this. Now let's move on to question number 4. Again, I will give you 10 minutes to solve, and then we can discuss the solution. So let's take a look on this question. So in this question, we have been stated that saturated steam at 0.14 bar is condensed in a shell and tube heat exchanger with one shell pass and two tube pass consisting of 130 blast tubes, each with length of per pass 2 meter. The tubes have inner and outer diameters of 13.4 mm and 15.9 mm respectively. Cooling water enters the tubes at 20 degrees Celsius with a mean velocity of 1.25 meter per second. The heat transfer coefficient for condensation on the outer surface of the tube is 1350 watt per meter square Kelvin. The overall heat transfer coefficient of the system is 1837.59 watt per meter square Kelvin. Determine the steam condensation rate. And then we have been given the formula for the effectiveness. So in this question, we have been given a shell and tube heat exchanger. And for the given parameters, we have been asked to find the steam condensation rate. So we can write the heat balances due to condensation. The heat exchange will be Q is equal to m dot h upon hfg, where m dot h is the condensation rate that we have to find. We know that this Q will be the heat exchanged by the cooled fluid. So it will be m dot Cp into C into temperature of cold fluid outlet minus temperature of cold fluid inlet. This m dot we have to find, m dot h we have to find, and upon hfg. Now in the given question, we have been given that cooling water enters at 20 degrees Celsius, that is Tc in is 20 degrees Celsius, but we haven't been given Tc out. So this term we need to calculate. So again, we can use the same correlation, that is Q is equal to mc Cp of cold fluid upon Tc0 minus of Tci to calculate Tc0. Now Q, we can calculate it from this effectiveness factor that we are having. So effectiveness, we define it as Q upon Q max. That implies that Q will be equal to epsilon times of Q max. So this we can replace over here. So we will be getting epsilon times Q max upon m dot Cp of C plus Tci is equal to Tc0. This we are having. Now for that, first we need to find the effectiveness factor also. So for effectiveness factor, we have been given this equation, that is epsilon is 1 minus exponential of minus of NTU. Now NTU, we know that it is nothing but UA upon C minimum. So now you can replace the values over here. So for that, first you need to find the C minimum. So for this case, C minimum is the per cold fluid, that is m dot Cp of cold fluid. The mass flow rate will be rho AV and average fluid velocity as well as the number of tubes. So this will be equal to the mass flow rate. So once you have this mass flow rate, then you can calculate the C minimum that you can put over here, and then you can obtain the value of NTU. So the value of density that we have been given is 995. The area will become pi dl. No, the area will become the cross-section area, that is pi by 4 d square. And the diameter is, inner diameter is 13.4 into 10 raised to minus 3 mm square. Velocity we have been given as 1.25 meter per second. The number of tubes are 130. So if you calculate this, the value of the mass flow rate should come around 22 kg per second. And from that you can calculate this NTU, that is UA upon CM, UA upon C minimum. So the value of U naught, the overall heat transfer coefficient, is 1837. Area will be pi d L, again into number of tubes, upon C minimum. We can calculate it from 22 into Cp of the cold fluid is water 4178. So if you calculate this, the value of NTU will come around 0.5. So from this 0.5, you can calculate the value of epsilon as 1 minus of exponential of minus of 0.5. This will come around 0.39. Now this effectiveness factor you can put over here. So epsilon, we have Qmax we need to calculate. So let's just do that. So it will be TC0 is equal to TCI, that is the inlet temperature. Inlet temperature is 20 degrees Celsius. 20 degrees Celsius plus epsilon times of Qmax. So Qmax we know it will be C minimum into THI minus of TH0. And upon we were having again this term m dot Cp, C of the cold fluid. So ultimately the C minimum will get cancelled out, and we will be having 20 degrees Celsius plus 0.39 into the temperature difference of the hot fluid inlet minus, this should be cold fluid inlet. Hot fluid inlet okay, so for here we are having steam, so we can just take it as 327 Kelvin minus the cold fluid will become 273 plus 20. So this will come around 306 Kelvin, the cold fluid outlet temperature. Now using this TC0, we can find the value of this mass flow rate, the condensation rate that was given. So you can just put the values as m dot required is, this is basically C minimum into, it was Tc0 minus of Tci upon HFG. Now we have this Tc0, we have this Tci, this we already calculated, and we have this HFG. So you can replace all those values over here, and you can get the mass flow rate as 0.54 kg per second. So you can take a quick look on the sample solution. Now let's move on to the fifth question. You can again read this question and then you can solve it in a couple of minutes. So let's take a look on the solution. So in this question, we have been given that a fin tube cross flow heat exchanger is, is to use the exhaust of a gas turbine to heat pressurized water. Laboratory measurements are performed on a prototype of the heat exchanger, which has a surface area of 10 meters square, to determine the overall heat transfer coefficient as a function of operating conditions. Measurements are made under particular conditions for which m dot h is equal to 2 kg per second, thi is equal to 325 degrees Celsius, m dot c is equal to 0.5 kg per second, and tci is equal to 25 degrees Celsius. And they reveal a water outlet temperature of Tc0 is equal to 150 degrees Celsius. So what is the overall heat transfer coefficient of the heat exchanger? And then we have been given the effectiveness formula by using the NTU. So in this question, we have been asked to find the overall heat transfer coefficient of the heat exchanger. So we can again use the NTU method in order to find the overall heat transfer coefficient. So basically we know that NTU is given as UA upon C minimum. So this is what U we have to find. But in order to find the NTU, we don't have any information about NTU. So what we can do is we can find the effectiveness factor. From the effectiveness factor, we can calculate the value of NTU. And once we have that NTU, we can put over here and then calculate the value of U. Now, in order to find the value of effectiveness, we know that effectiveness is given as Q upon Q max, where Q will be, let's consider the cold fluid, Cc upon Tc0 minus of Tci upon Q max will be again C minimum upon Th inlet minus of Tc inlet. Now we can replace the desired values in order to find the effectiveness factor. So we don't know what is C minimum. So we can just calculate both of these terms, that is Cc for the cold fluid will be m dot Cp of the cold fluid. Similarly, Ch for the hot fluid will be m dot Cp upon H. So for cold fluid, the mass flow rate is 0.5 and the temperature and the heat capacity is this 4203. It will be 0.5 into 4203. So this will come around 2101.5. Similarly, for the hot fluid, it will be 2 into 1040. So it will be 2080 watt per Kelvin. So we can take this as the C minimum. Again, now over here you can see that both of this will get cancelled out. And we can find the effectiveness by putting the values of the temperature. So it will be Tci is 25, Tc0 is 150. That is 150 minus 25 upon 325 minus of Tci is 25. That is 125 upon 300. So we will be getting the value of this as 0.42, the value of effectiveness is 0.42. Now we can put, now in order to use this formula, we also need to find the CR. So CR is nothing but the ratio of C minimum upon C max. The CR will become the ratio of both of this term, 2101.5 upon 2080. So this, no, it should be so it should basically inverse of this because C minimum is 2080. So this will come around 0.99. So this 0.99 you need to put over here, and you we have to find an epsilon you can put over here, and then you can try solving this by trial and error. So this will give you the value of NTU as 0.8125. So from this NTU, you can put over here, and we have this area given as 10 meters square, that is U into 10 upon C minimum. We calculated it as 2080. Then you can just calculate the value of U as 0.8125. One thing to notice over here, the C minimum will be the hot fluid. So this won't get cancelled out, but since both of these terms are similar, we are cancelling it out. Earlier I had incorrectly mentioned that it's C minimum versus CC, but no, in this case C minimum will be the CH. That was a minor correction. And from this, the value of U you can calculate as 169. So from this, you can get the value of U, that's the overall heat transfer coefficient, as 169. So that was the question number 5th. So other questions are very similar to this. So let's just see this question number 6. You can try reading it on your own, and then maybe I will share the solution with you. Let's see this question. So in this question, we have been given that hot air for large-scale drying operation is to be produced by routing the air over a tube bank, while products of combustion are routed through the tubes. The surface area of the cross-flow heat exchanger is 25 meters square, and for the proposed operating conditions, the manufacturer specifies an overall heat transfer coefficient of U is equal to 35 watt per meter square Kelvin. The air and the combustion gases may each be assumed to have a specific heat of Cp is equal to 1040 joule per kg Kelvin. Consider conditions for which combustion gases flowing at 1 kg per second enter the heat exchanger at 800 Kelvin, while air at 5 kg per second has an inlet temperature of 300 Kelvin. What are the air and gas outlet temperatures? So this was the question. And we have been again given a different formula for this effectiveness based NTU and effectiveness calculated using NTU. So in this question, you have to find the air gas and outlet temperatures. So basically, we have been asked to find TCO as well as TCH outlet. So in order to calculate this effectiveness based, first we need to find C minimum, C basically both the C minimum as well as C maximum, and from that we can calculate the value of NTU. From that again we can calculate the effectiveness, and then on the basis of the effectiveness, that is the formula of effectiveness. Basically the formula of effectiveness is given as Q upon Q max, where Q can be CH into TH inlet minus TH outlet upon C minimum upon TH inlet minus of TC inlet. This can also be equal to CC upon TC outlet minus TC inlet upon C minimum TH out upon TCI. So for that we need to find the effectiveness factors. CC, C minimum we will be having. Then the remaining parameters we will be having, and on the basis of that we can just equate both of these two equations and then find the formula. Basically what else we can do, we can just calculate the value of C. Since we are having HI, CI, we can calculate the outlet temperatures. So first step is to calculate C minimum as well as C maximum. So let's just consider this will be m dot Cp of what fluid. So since the mass flow rate is 1, combustion gases has the mass flow rate of 1, and their Cp is 1040. That is m dot Cp will be 1040. Similarly, for the air, it will be 5 into, both are having the same value. That is 5 into 1040, that is 5200. So CR for this case will become 1040 upon 5200 is equal to 0.2. And TU, you can calculate it as UA upon C minimum. The value of U we have been given as 35. Value of A we have been given as 25. Value of C minimum we have over here 1040. So this you can calculate it as 35 into 25 divided by 1040 as 0.841. So this 0.841 you can put over here along with CR, and you will be getting the value of effectiveness factor as 0.537. So you can try calculating the effectiveness factor from the given formula. So once you have this effectiveness factor, you can just write from these equations, that is TH0 is equal to THI minus of epsilon this Q max upon this CH. Similarly, for the cold fluid, you can write TC0 is equal to TCI minus epsilon upon Q max upon CC. So this TH inlet we have been given as 800 and TC inlet is 300. So this will be 800. 300 epsilon we calculate as 0.537. Q max you can calculate. CH we already calculated, and you can just replace the values and the value of TH0 will come around 531, and the value of TC0 will come around 353.7 Kelvin. That was the final answer, whereby we are using this effectiveness based NTU based effectiveness in order to find the outlet temperature of the cold fluid as well as hot fluid. So this is the solution. You can take a look on into this. So if you have any doubt, you can just unmute yourself and ask. So this is the last question for today's. After this, we can end the session. Well, let's move on to, I think this much is sufficient. I think we can take one more question. So you can try solving this question number 7, and then I will just share the solution with you. So let's see the solution of this question. So in this question, we have been given that a Shell tube heat exchanger is to heat an acidic liquid that flows in unfinned tubes of inside and outside diameter di equal to 10 mm and d naught equal to 11 mm respectively. A hot gas flows on the cell side. To avoid corrosion of the tube material, the engineer may specify either a nickel chromium molybdenum corrosion resistant metal alloy with the given properties or a polyvinyl fluoride plastic with the given properties. The inner and outer heat transfer coefficients are HI is equal to this 1500 watt per meter square Kelvin and H naught equal to 200 watt per meter square Kelvin. With the following assumptions, what is the ratio of plastic to metal tube surface areas needed to transfer the same amount of heat? And what is the ratio of plastic to metal mass associated with the two heat exchanger designs? So basically, what we have been asked to find is in the first question, we have been asked to find the area of plastic upon area of metal, ratio of area of plastic area of metal, and second question, you have to find the mass of plastic upon mass of metal. Now, we can calculate the overall heat transfer area by using the overall heat transfer coefficient. So for this Shell tube heat exchanger, we can write the overall heat transfer coefficient as 1 upon UA is equal to, for inner side, it will become 1 upon HI into AI. AI will be pi DI upon L, plus for outer side, it will be 1 upon H naught pi D0 and L. And due to conduction, it will become ln of D naught upon DI upon 2 pi KWL. So from this, we can calculate the value of UA for both this plastic as well as metal. So let's just calculate. See, over here you can see that the first term and second term will remain same for both the material, only the last term will differ. So ultimately, this is our convection of inlet, resistance of convection due to outlet, and R of conduction. So our conduction is the only thing that will differ between both of this metal as well as plastic. So our convection you can calculate as 1 upon HI pi DI. So L you can just take common from each of those terms. So we can just calculate this term 1 upon H. So HI is given as 1500 into 3.141 into DI is 10 mm. So from this you can get the value of our convection inlet as 0.0212. Similarly, our convection outlet, you can calculate it as 1 upon H naught pi D naught, and this should come around 0.1447. Now our conduction for metal and plastic will be different. So our conduction for metal, you can just put the value of Kw for metal as this term, and for plastic you can put the value as this term. And if you put those values, the value of our conduction for metal will come around 0.0019, as well as for plastic it will come around 0.0892. So basically what we can write is 1 upon UA is nothing but our convection inlet plus 1 upon our convection outlet plus 1 upon our conduction. For if this is for metal, If this is for metal, so this will be all for metal. So in order to find the ratio of area, we can just take the ratio of both of this term and U will be same. So area of metal upon area of plastic. No, in this question we have been asked to find the reverse, that is area of plastic upon area of metal will become R convolution inlet convection outlet plus R conduction of metal. Similarly, this will be this plus R conduction of plastic. So you can put all those values in, you can find this ratio, and then in order to find the ratio of mass, you can just multiply them by their densities. That is MP upon MM will become rho P AP upon rho M AM. This is what you can calculate. From that you can get the final answers. So if you have any doubt, you can just ask. I will be here for 5-10 minutes, or else we can end today's session.